Today we're going to talk about the polynomial time hierarchy some more in a couple of different ways. First, we're going to talk about a different definition of it involving oracles. Oracles will recur a few times in this course. We'll also connect it somewhat with polynomial-sized circuits, circuit families. Let me start with like a little story or a parable or imaginary scenario. So let's imagine that Alice proves that P does not equal NP. It's great. So she comes up with like an actually efficient algorithm for solving SAT. And she's very happy. Or if you don't like this parable, you think it's too unbelievable, you could just imagine that she works in verification and she has like a really great SAT algorithm that she seems to think maybe correctly that works well on many, many instances. So she can solve SAT and she goes crazy and she starts solving SAT formulas. And she can also decide if formulas are unsatisfiable or if they're tautologies. And she can tell if two circuits compute the same Boolean function. And she can go further, as we saw last time, she can tell if a circuit is like the smallest circuit computing some function. That was the min circuit problem. She can just go nuts. She can solve efficiently anything in the polynomial time hierarchy. Okay, so now let's imagine Bob wants to get on the action, so he asks Alice for the algorithm, and she gives him, she doesn't want to give all away her secrets, so she gives him just like a black box that will do it for him. She puts the algorithm inside a box and says, here you go. You can put any input you want into this, and it'll give you the output of my algorithm. And so now he also can solve SAT problems. His black box is the same input-output behavior as her algorithm, so he can start solving SAT formulas. That's great. He can decide if formulas are unsatisfiable. That's great. He can decide if circuits, two circuits compute the same function. That's great. So he feels he's as powerful as Alice. So then he says, all right, great. I'm going to solve the min circuit language. I'm going to take a circuit and decide if it's the smallest circuit, solving that language or deciding that language or that Boolean function. But he's a little stuck. What is he going to do? So imagine he's got the SAT, the SAT algorithm. It's really efficient. It's right there in his hand. And he's got a circuit. And he wants to know whether or not there's a smaller circuit that computes the same function. What's he going to do? It's funny because Alice can do it. But if you think about it, what is Bob going to do? See, if you remember, what's the deal with the minimum circuit problem? C is in this language, a minimal circuit, if and only if, let me write it slightly informally, but for all C prime that are smaller, I'll write this for the size of C. It's not the case that C and C prime are equivalent. So Bob, with this black box for solving SAT, for deciding SAT instances, you give him any two C and C prime. This is basically to say the two circuits, this is like a SAT problem, right? To say the two circuits are not equivalent is to say that there's some string where they differ. You can encode that if you've got C and C prime as like a SAT formula or a circuit SAT problem, and you can use your black box to solve any instance like this. But what Bob really has is like one C, and he wants to decide this. And what's he going to plug in to his box? He doesn't know. You see, there's a difference. Alice can solve this problem in polynomial time. And why can she do it? This problem is in NP, so it's equivalent to like a SAT formula.
What's Alice's goal?
Alice's goal is to also decide if solve instances of the minimum circuit problem. She can do it, right? This language is in the hierarchy. So as the person that proved that P equals NP, she can also get polynomial time algorithms for solving questions that look like this. Yeah.
I think the difference is that she can encode this oracle thing in the string that she puts inside the oracle. So.
That's right. That's right. So this isn't, for any, this is like an NP problem given C and C prime. But Alice has, proved that NP equals NP. So she has code that solves SAT problems. So she can write down a polynomial size formula that expresses the statement that these two things are not equivalent. Because she can convert that like an NP type statement into like a polynomial size formula. And so she can then form this as a sentence that's just as like one quantifier for all C prime. And then some polynomial size deterministic formula, or like, that will involve like the code of her SAT solving algorithm in some sense. And then she can ask, the SAT question about this formula. But Bob cannot do that. He does not know the code for this SAT algorithm. I mean, he just has the ability to answer these questions, but like he cannot express this as like just a simple unsat problem, because he cannot like express this with like a polynomial size formula. So the point of this parable is like it's better to have having code for an algorithm is better than having a black box that can do the algorithm. Does that make sense? So we want to actually formalize what is the difference. So we want to talk about how you can formalize Bob's role, or Bob's position, where he has like the ability to solve SAT problems, but like it's not because P equals NP necessarily. It's just somehow he has like a magic box that will answer SAT problems for him, which is less powerful than like actually knowing a polynomial time algorithm that will solve SAT. Okay, so this leads us to the notion, which perhaps you've seen before, of an oracle, or an oracle Turing machine. Actually, the homework references it, so hopefully you've seen it before. So a Turing machine, M, with an oracle, or black box, you can think of it, for language L, like SAT, for example. Well, it's like a fictional model of computation. It's like, say like M is like a TM, but like it has also a special tape called an oracle tape that it can write to. Sometimes if you're being extremely careful, you insist that it's like write only, but we don't need to get into such things. And it also has an oracle state. Turing machines have states, this like state diagram that looks like a DFA. So it has normal states, accept state, reject state, but now it also gets like an oracle state. And what is the semantics? When the Turing machine enters the oracle state, what happens? So when it enters the oracle state, basically it learns whether what's written on its tape is in the language. State, we can say like, the oracle, let's say with X written on the oracle tape. Let me write Y just to not confuse it with the input. You can just imagine, the oracle tape is replaced by the answer to, 1 or 0, depending as whether Y is in L or not. Okay, so that formalizes the idea that, like, if you have an oracle or black box for language L, like basically, it's like an algorithm, but like in one step, it can get the answer to questions about whether a given string is in L. But for simplicity, we just count like these oracle queries as one step because, it takes you an amount of time to just write down your query anyway. So like, we're fine with that. Yep.
So are you saying that Y is replaced on the tape with 1 or 0? But I thought you said the oracle tape was right.
Well, it's a magical tape. I mean, you can either you can just also imagine that, like, the oracle state has 2 outcoming transitions, one for like when it's in the language, one when it comes out the language. I wrote this way because other people, like, if you're being very finicky about like the best way to define oracles, the best way to define them for various technical reasons is the oracle tape gets erased after you make a query about it. So if you're really careful about like defining oracle Turing machines with space classes, like that's a better assumption. So I just combined it all for fun into like one statement that like has the oracle tape get erased once you make your query. I mean, of course, you have like multiple tapes, right? So you can like, before you query the oracle, you can like save what you wrote on the oracle tape to some other tape, and then it's as if it didn't get erased. But if you really care about like space efficiency, then maybe you prefer a different model. Okay, so the notation here is, so really I kind of combined 2 things with one definition. Like really, there's a notion of an oracle Turing machine, and you often write like M superscript question mark for like an oracle Turing machine. That's like an oracle machine. And then, like, given an oracle machine, you can instantiate the oracle with various languages. So like if then, L is a language, you'll write like M to the L. and then maybe computing on a string x. Okay, so in some sense, there's a definition of an oracle machine separate from the oracle language itself. Okay, so in this story I told at the beginning of the lecture, I'll write definition without actually writing any words because I think it's kind of clear. I imagine Bob has the power of p to the set. So Bob can be any polynomial time Turing machine with a SAT oracle. And this is a class of languages, the problems that can be solved in polynomial time if you hypothetically had a SAT oracle. And one thing that I was talking about there is the fact that it's not clear whether the circuit minimization problem is in this class. Yeah, I'll tell you, it's believed to actually not be in this class. Okay, any questions? Let me put down some more notation. You'll see p to the np. This is formally defined as it's the union over p to the l for all languages L that are in np. So it's like everything you could solve with an oracle for your fixed NP language, any fixed NP language. But actually, these are the same thing. Okay, these are actually equal. And of course, this is a subset of this because SAT is an NP, so you can always choose SAT to be your NP complete language that use an oracle. But conversely, we know by Cook's theorem that every language in NP, many one reduces to SAT. Okay, let me not write this, but every language in NP, many one reduces to SAT. So if you can solve some problem in polynomial time using like a oracle L that's in NP, and just before you ask the L query, run the reduction from L to SAT and ask about the reduced string instead. Okay, so as long as we don't care too much about running time, we say it's it's polynomial running time, you can run the many one reduction before you ask any L query and turn it into a SAT query. Does that make sense? So I'll use these two notations interchangeably. Sometimes I'll write p to the np, sometimes I'll write p to the SAT. Okay. In fact, to say some more notation, we're going to focus on this language for a while. So we're going to ask ourselves, what's going on with this class, p to the SAT? What is it? And another way to phrase it is it's all the languages, I don't want to get into this too much, that are, but let me say it now, that are Turing reducible to SAT. Sometimes called Cook reducible to SAT. Right. So sometimes when you're studying basic, theoretical computer science, they tell you the less good definition of reductions. We'll say that a problem reduces to SAT if you can, there's a polynomial time algorithm that solves the language, assuming you have the ability to solve SAT queries. That's not a great definition of reducibility. It's okay. That's Turing reducibility. The one about many one reductions it's better. But if that other definition is exactly this, it's like your polynomial time, and you can you imagine that you can answer any SAT questions you want. That's to say that you're Turing reducible to SAT. Okay? And one reason we like actually many one reducibility is that NP is closed under it. So if B is an NP, and A many one reduces to B, then A is also an NP. But that's not true with this notion. And in fact, we know, of course, that certainly any language in NP is NP to the NP. But also, for example, unsat is NP to the NP. Right? If I have a formula, I want to know if it's unsatisfiable. I can do that with, let me write SAT here. I can do that with the SAT oracle. I just ask the SAT oracle, hey, is this satisfiable or not? Yes or no? And then I output the opposite of that. Okay? So one observation to take away from that, it'll come up a couple times in this class, is if you have an oracle for a language, it's equivalent in power to having the oracle for the complement of the language. So you can just always reverse the answers of the oracle that you get. So unsat is also in this class, p to the SAT. So unsat is Cohen p complete. So you can easily check, therefore, that Cohen p is also a subset of this class. So this is a funny class. It contains NP and it contains Cohen p. Okay, so there's a picture we can draw that looks like this. The rightward going lines are inclusion here. Right, so we have this picture. P is a subset of NP and CoNP, and they're both subsets of P to NP. And on the other hand, this is unclear, and as we'll get into, like, this is actually a class that sits somewhat low down in the polynomial time hierarchy. Okay, questions? Okay, so yeah, so seemingly, circuit minimization is not in PSAT, and like in particular, pH seemingly does not equal P to the NP. This is like saying, okay, we don't know how to prove this, but they could all be, P space could equal P, but this is like the power of Alice in the story at the beginning of the lecture, and this is the power of Bob, and like, this one seems to be better. It has this problem in it, for example. Now, on the subject of like this circuit minimization problem, let's think about like its complexity again a little bit. Here's something that I claim. So let's double check this. I claim that it'll be a little, instead of talking about circuit, minimal circuit problem, it'll be slightly easier for me to talk about the complement of this language, all the circuits which are non-minimal, all the circuits where there's a smaller circuit that does the same job. I claim that this is in the following complexity class: NP to the language equivalent circuit. Okay, so here I'm extending the notation a little bit. This is all the problems that can be solved in non-deterministic polynomial time when you also allow the non-deterministic polynomial time algorithm an oracle for this language, the equivalent circuit language. Now, what is the complexity of the equivalent circuit language? If I give you two circuits and I want to know if they compute the same function, that's in CoNP, right? That's a CoNP type question. It's like for all strings, the circuits output the same thing. So it's a CoNP complete language. So this is, it's equal to, in fact, it's contained in fact, equal by virtue of the CoNP completeness of this. This is NP to the CoNP. Sorry, I should, before jumping into that, let me justify why this is true. We kind of talked about this before, but why is it true that a non-deterministic polynomial time Turing machine with this equivalent circuit oracle can solve this language? Well, it's sort of the idea we talked about last time, right? So the machine, it non-deterministically guesses the smaller C prime, given C, and then checks that C is equivalent to C prime using the oracle. In fact, this is actually nice. This algorithm that solves this language with a polytime non-deterministic machine in the oracle, it actually only used the oracle one time. Actually, you can use the oracle, in the definition, as many times as you have time for. This algorithm happens to only use it one time. And actually, it's not a coincidence, as we'll later see. OK, so as I mentioned before, sorry, was there a question?
Yeah, like a little bit, but can you explain one more time why socket min is not in PSAT?
I can't prove it because it's not known.
No, well, just explain like
the idea?
So the socket mean, we have to check that for all smaller sockets something is true.
Yeah.
For all smaller sockets, it's like CoNP statement, right?
Yeah, now you're getting a little slippery, but yes.
Okay, so we can write a CoNP Turing machine for solving that using equivalent circuits?
No, we can only write like a CoNP machine that decides circuit minimization if we know how to basically express this with a polynomial sized circuit.
We can express this in like all of one circuit using SAT.
We can express this using like a very small circuit if we allow the circuit to have oracle gates for this language.
Right, but we have this oracle like right on the upper level. We have the oracle for SAT, so we can use it in the lower level as well.
A Turing machine that is a P to the SAT Turing machine has oracles, right? But it's simply not the case that this is like a for all type, like this statement is like not, when it's not like a first order logic statement with a polynomial size formula here. It's like a first order, quantified statement with a weird object here, like a formula that has like equivsat oracle gates in it. So it's not in CoMP. I mean, that's not, you're not allowed to like, you're allowed to write down like first order formulas that start with a for all and like have like basic propositional logic here. That's in CoMP, deciding those. You're not allowed to have like weird gates inside here. The point is like, if you happen to prove that NP equals P, then there exists an equivalent polynomial size circuit or formula that expresses this concept. And therefore, like there exists, a way to write this such that this piece is just like a normal propositional Boolean formula.
Yeah, I mean, that's, but if I just have a black box SAT, I cannot do that.
Basically, the only thing I could say is, as I'm talking for the next 20 minutes, just like, what are you going to do? Like, think about, try to think of an algorithm for this problem that is, just gets rid of the non-determinism here. It's just a regular polynomial time algorithm with an oracle for your favorite NP language. You'll get stuck. Yeah, I mean, yeah, it's not the easiest thing to immediately grasp, but. OK, one thing I mentioned here a couple times is like having an oracle for a language L. It's identical in power to having an oracle for the complementary language, because you can just reverse the answers you get back from the oracle. That's also a bit different from NP, right, and like non-determinism, but it's a thing about oracles. So actually, this class, everything that a non-deterministic machine can have using a language in CoNP as an oracle is also equal to this class, NP to the NP. It's funny, but like it's, you can having an oracle for the complement is the same. And this is also the same as NP to the SAT, because you may as well have an oracle for the SAT language. SAT is NP complete. So all these 4 classes really are the same class. And it's like it's a different class than this. It's like you're a polynomial time non-deterministic machine, and you have oracle access for some NP complete language like SAT. And I want to focus now a little bit on like what is this class? Or I could have circled everything, but like it's usually written more like one of these 2 things. So what's up with this class? No, it's not just, yeah, you might think like it should just be NP, right? But it's probably not, because it contains, for example, the non-circuit minimization problem. And that doesn't seem like it's in NP. I mean, it doesn't even seem like it's in P to the SAT, which contains NP. So yeah, despite the notation, like it's different. And part of it is because you have the ability to like reverse answers. Like if you're a non-deterministic machine and like you had NP queries, but somehow like maybe you got one NP query at the end and you had to go with whatever the oracle says as your final answer, that would be NP. But because you have the ability to say like, oh, I'm going to like reverse the oracle's answer and like use that to accept or reject, that makes a difference. So in fact, this class is sigma 2p, as I'll prove to you. That was proved by Celia Rathhall in 1976, not too long after the invention of the polynomial time hierarchy. In fact, Stockmeyer and Meyer, who invented the polynomial time hierarchy, defined it in terms of oracle machines and like NP to the NP. And the version we saw last time with kind of like for all exists sort of statements, that was sort of her alternate way of looking at it. But they're equivalent. So this gives like an alternate way, as I said, to define the polynomial time hierarchy. So here's some theorems. So one, as I said, sigma 2p equals np to the np. Well, let me write it like this, np to the sigma 1p. Okay, that's another notation for np. Okay, that's true. It's also true that like pi 2p equals CoNP to the sigma 1p. As you'll see, like the important thing is like what is the nature NP or CoNP of the base of the action here when you're trying to just look at sigma versus pi here. So further in general, like sigma 3 to the p is sigma 3p. This class is np to the with an oracle for sigma 2p. And pi 3 is Cohen p with an oracle for this sigma 2p. Doesn't matter if I write sigma 2p or pi 2p here, because having an oracle for a language is the same as having an oracle for its complements, and so forth. Sigma ip, as we defined it last time, is the same as np with an oracle for sigma I. Let me say sigma I plus 1p is the same as np with an oracle for sigma ip. So another way to define all the polynomial time hierarchy with oracles. And for the proof is, well, the proof of the full thing is by induction on I, as you might expect. But I'll just show the first one, star, meaning this. And that's kind of like what I'm about to show you is like the proof of the inductive step, basically. So you'll get the gist of it from star. Okay, so what do we actually have to prove here? Like, what's going on? Well, we're trying to show that two classes, which have been decided in separate ways, are actually the same class. So a class is a collection of languages. So we have to show two directions. So the first thing we want to show is sigma 2p is a subset of np to the np. Okay, and this one is basically easy. Okay, this is the same as np to the sat. It's np to the unsat, or tautology. Okay, so why is this easy? Well, you actually kind of have like more power than you need in order to decide this. So for example, one thing we saw last time is that a complete language for this class is like sigma I sat, or sigma 2 sat. So it's like deciding statements that look like there exists x, such that for all y, some formula involving the variables in x and the variable y is true. So deciding statements that look like this, or this is just a basic propositional logic statement, that problem is complete for sigma 2p. So we just have to decide, we have to show that, deciding whether a statement like this is true or not can be done by a polynomial time, non-deterministic Turing machine with, you can say, an unsat oracle. And that's fine. So, right? You just, well, you use your non-determinism to handle this part. So non-deterministically, universally guess x. You're trying to verify that this is true. You like guess the x that makes the sentence true. And then you're left with checking that this part for all y, phi xy, where these are now fixed 0, 1 values, is true. In other words, that like phi with x fixed and y as variables is a tautology. And you just ask the oracle about this. Okay? So you use your tautology oracle. Or, if you like, you can like negate phi xy and ask a sat oracle, is this satisfiable? If it is, then you know that for all y, phi xy is false. Okay, to decide, well, to verify if this part for all y, phi xy is true. Okay, what it really means is the non-deterministic machine, guesses, uses existential guessing to guess x, and then it accepts or rejects based on what the tautology oracle tells it. Okay, and then it's true that the non-deterministic machine overall accepts, in the sense that at least one of the computation branches accepts, if and only if this is a true statement. Any questions about this? Okay, let's talk about the other direction then. Why is np to the sat a subset of sigma 2p. So why is this hard? Why is this non-obvious? Well, basically, sigma 2p, if you think of, let's say, the alternation version of it, is like you can universally guess some stuff, and then you kind of, existentially guess some stuff, and universally guess some stuff and check. So it's kind of like you can kind of existentially guess some stuff or use non-determinism, and then you kind of like get one for all statement that you can sort of check. So in fact, what we're going to show to prove this is that we'll show, but I should say in contrast, like here you got like universal guessing, but you can go crazy and ask like tons and tons of SAT problems, unsat problems. They're all mixed together. What we'll show is that actually having the ability to ask lots and lots of SAT questions is not that powerful in the context of non-determinism. We'll show that like actually NP to the SAT is like a subset of a seemingly restrictive class, MP, let's say with, okay, if I just change that to unsat, no big deal, but let me say, I'll put this notation in, meaning you only get one unsat query. And not only that, you get like one unsat query at the end, and then like if it says yes, you have to accept. If it says no, you have to reject. So like you don't get to reverse it or anything. Like the very last thing you do is like make an unsat query and go with it. So you can do that in NP to the SAT, but it seems like you can do a lot more stuff than that. But I'm going to show this. And then in some sense, it's kind of clear that this is a subset of sigma 2p. Let's say if you think of the alternating Turing machine version of this, both these models can do some like existential guessing for a while, and then like the last thing this thing does is like it has a formula and it wants to check like for all x phi statement about it. Okay, and it's just going to go with the answer, and with alternating Turing machines, you can use your universal guessing to do that last unsat check. Okay, so this is the key thing. Great. So how are we going to do that? So like you should imagine that you have some language decided, let's NP to the SAT. We want to show that it's also in this seemingly more restrictive class. So let M SAT be a machine, a non-deterministic polynomial time machine. Okay, so we have some polynomial time non-deterministic machine that has access to a SAT oracle that decides some language. I want to show that that language is also in here. I'll just describe how you can modify M so that it actually is like a one-query machine. Okay, so like, at first, like M's going along, it's, non-deterministically guessing some stuff. That's fine. But then it asks a query. And we don't want to just ask the query. Like we have to save up all our queries for like one unsat query at the end. So what should this simulation do? It's M asks a query. Yeah, so it's the game always with non-determinism, right? Like you're always beating the system by guessing. So like just have, in fact, you can even have it guess what it's going to query. If you like, you can like have it, guess all the queries and answers that it's going to make. But the important thing is the answers. It would make and get, at first. And then like it can start actually doing what M does, and like it can check that the string it queried the SAT oracle on is something that it guessed. But it can also, that's fine, and reject if not. And then it just proceeds as though the answer it guessed was the correct answer. Okay, so it proceeds as though all its guessed answers are correct. So, but at the end, it has to like check all the answers are correct. Okay, So at the end, half of its job is easy. So at the end, it does the following. You see, for the formulas, it guessed a yes answer, i.e. that these guys are satisfiable. Well, it's a non-deterministic machine, so it can guess satisfying assignments for them. Guess and verify satisfying assignments for each. Okay, and here again we're relying on the fact that the notion of when an overall non-deterministic computation it accepts is only if if it finds some branch that accepts. So if it on some computation branch it guessed that phi2 was a yes answer, and then at this part it guesses a satisfying assignment for phi2, but that guess doesn't satisfy phi2, then it just locally rejects. Okay, and that's sort of fine. If these guys really are all satisfiable as desired, then there's one magic branch where in this stage you correctly guessed all the satisfying assignments for these satisfiable guys, and that's the one local acceptance that works. Yeah.
Does this have to happen at the end, the part for the yes, or can the yes just
Doesn't have to happen at the end. Good point. So this part you could have done as you went along. Yeah. So here it's going along. And if it says, oh, I'm querying this formula, and I guessed that it's an accepting formula, it can just guess and check the satisfying assignment for that formula phi2 right then and there, and preemptively reject if its guess is not it. Yeah. So the next part for the verifying the no answers, that's what we do in one shot at the end. Okay. For the no answers, it's a little trickier. Let's say for formulas phi1, phi2, etc. So a bunch of the formulas that this guy was going to query on, the phi's, maybe it guessed that these were not satisfiable. So it cannot check that using its own non-determinism, but hopefully it can check that using its oracle. And it only gets one oracle call, but that's OK, because it wants to simultaneously confirm that all of these guys are not satisfiable. So what does it do? Yeah, it ORs them together. So it forms, let's say, capital phi, which is the OR of them. Okay, and it uses its one unsat query to verify that this thing is unsatisfiable. And not only that, but it just goes with the answer to the oracle query. This is the very final step. Whatever the oracle tells me, yes or no, I'll accept or reject. Okay. And if indeed they are all unsatisfiable, then the oracle will say yes, and so the overall non-deterministic computation will locally accept, and that's the one branch that makes the whole thing accept. Okay. Any questions about this? Okay, so henceforth, we'll remember all these different definitions of the hierarchy. And obviously, when we're trying to show something is in the hierarchy, it's to our advantage to use this oracle-based definition because it's syntactically looking like the most powerful one. And conversely, if we want to show that the hierarchy is not too powerful, that it's contained in something, then it's more convenient to use this weaker notion where it's defined by, let's say, this being the complete language. Okay, so I want to actually sort of switch topics a little bit now. We've spent a long time talking about the polynomial time hierarchy, which might look like a bit of an abstruse concept. So why do we care about it so much? Well, basically it helps us reason, as you'll see, about the things that we really care about, like polynomial time and just sat in P. And sometimes in order to gain insights about these questions, we have to pass through some more funny-looking concepts. So another good thing it's useful for, as we'll see in the rest of this lecture, is teaching us about the relationship between uniform and non-uniform computation, how they're different. So circuits versus Turing machines. That's what I'll talk about in the rest of this lecture. Okay, so NP contained in P is disbelieved generally. But what about, I mean, we're just happy to assume that. But what about NP contained in P/poly? This is much bigger, right? This has undecidable languages in it. So maybe it might look more believable. But then on the other hand, you know, it's the same as polynomial size circuit. So it's basically like just this, you know, this is like asking about the possibility that, you know, SAT has polynomial size circuit families. So it's like the one advantage you get over here is that for each different formula length, you can have a different polynomial time algorithm. That doesn't actually seem that helpful because, like, you know, how is it going to be like helpful? You'd have a different like algorithm for length 1,000 inputs than length 1,001 inputs for SAT. But still, we might want like better evidence than that for the unbelievability of this. Than just say like, well, it doesn't seem like it's any more powerful. So better evidence for this, you know, showing that even this non-uniformity, this is not helpful in the context of, let's say, computing SAT or NP, comes from a famous theorem in complexity from around the early 80s called the Karp-Lipton theorem. Okay, which we will prove today. It's a great theorem. It just says this. If NP is contained in P/poly, then the polynomial time hierarchy collapses. Okay, so this is some consequence we talked about last time that you know, it's generally disbelieved. It's, you know, it's stronger than P does not equal NP, but it's a pretty believable hypothesis. And the nice thing here is this is like a uniform. This is only talking about uniform models of computation, complexity, you know, Turing machine-based complexity classes. Okay, so it's telling us that even this non-uniform thing is very unlikely. Yep. Oh, you might want to know. So it collapses, in fact, more strongly to the second level. In fact, i.e., pH equals sigma 2p. And it's closer to complement, so of course it also equals pi 2p. If you really want to get like, you know, excited, it equals the intersection of these two things. Well, they're the same. Is there a question? Okay. The proof of the Karp-Lipton theorem is actually like 3 lines long once you have some reminders and preparation. And I guess you have, hopefully, these reminders and preparation from solving problem 1 on homework 3, or maybe you learned it in an undergraduate complexity class. Basically relies on some facts, which I'll remind you of now. The main one being that SAT is self-reducible, or downward self-reducible is one aspect of it. So this is a phrase we'll probably see later in the course. So I'll bring it up now. SAT has this nice property that it's downward self-reducible. What does that mean? Informally, it means that like if you have the ability to solve SAT on formulas of length strictly less than n, then you can also efficiently solve it on formulas of length n. So to invent some crazy notation, this is not exactly proper notation, but SAT is in P to the like SAT intersect. Okay, let me just say less than n. Okay, this is not proper notation, but if you want to solve, you know, SAT instances of bit length n, you can solve it in polynomial time, you know, given like the oracle ability to solve SAT instances of shorter length. And you remember how to do that, right? Like you got some SAT instance phi, you want to know if it's satisfiable or not. Basically, you like try setting x1 to 1. And that kind of collapses the formula a little bit to a shorter formula. And then you find out if that's satisfiable or not. If it is satisfiable, you know, with a trustworthy oracle, then you're like, great, the original one is satisfiable. If it's not, then you try also setting x1 to 0, which makes the formula shorter. You find out if that's satisfiable. If it is, you're like, great, the original formula is satisfiable. But if they're both unsat, regardless of whether you set x1 to be 0 or 1, then you're like, well, the whole thing is unsatisfiable because it's unsatisfiable both when x1 is 1 and when it's 0. So that's a beautiful property of SAT that we know and love. A very related property is that SAT has this property called efficient search to decision reduction. Okay, what does that mean? Well, there's something slightly artificial about the way we define SAT as a decision problem. Given a formula phi, is it satisfiable or not? really in life, you want to, like, given a formula phi, you want to find out if it's unsatisfiable or not. But also, if it's satisfiable, you want a satisfying assignment. Okay? And we mostly focus on the decision problem, satisfiable or not. But in life, we probably also want the search problem, find the satisfying assignment or a satisfying assignment when the formula is satisfiable. And one reason that we don't stress out about this distinction that much is because there's an easy reduction from the search problem to the decision problem. And it's basically the same downward self-reducibility trick. So given, let's say, a formula phi with bit complexity n, what we really want in life is the following. I'll put it like in braces and star it. We want to output now if phi is unsatisfiable. But if it is satisfiable, we want to output a satisfying assignment. Okay, else. And as I said, the point is that we can get this thing that we want, star, just from the ability to solve the decision problem. Okay, so the point is that we can get star, in Poly time, given, to use the same like funky notation, to write it informally, an oracle for SAT on strings of length less than n. And it's the same procedure, right? You give me your formula phi, you try setting x1 to 0, and you try setting it to 1, and you sort of ask the oracle both times, hey, is it satisfiable in these two cases? And again, if the oracle says it's not satisfiable in either case, then you know your whole thing is unsatisfiable. Otherwise, for at least one of the two settings, it tells you, yep, it's still satisfiable, even with that setting of like x1 to be whatever, 1 or 0. And then you recurse. Like you know like an acceptable setting for the first variable, and you recursively do the same thing to find acceptable settings for all the variables. Okay, and the nice thing about this, right, is like it's sort of self-certifying. When like your algorithm comes back and says like it's SAT, it like gives you a certificate that's like very convincing if you no longer have any weird oracle or non-deterministic powers that the formula really is satisfiable. There's one more like very important and simple property of SAT, which is the least important one to dwell on. But SAT, let me just write it like this. Under an appropriate encoding, is patable. And what do I mean by that? Again, I'll maybe explain it in words more so than just writing something. But basically, given formula phi of length, encoding length n, you can make an equivalent longer formula. Okay. Maybe you don't have this property depending on how you choose to encode SAT. Informally, you take a formula, you want to know if it's satisfiable or not. You can put some like junk unsatisfiable stuff at the end, like I don't know, make up a new variable x0 and say like x0 and not x0. Just that'll artificially make the thing longer, but not change its satisfiability. More formally, maybe you like alter the definition of SAT, so like it literally, phi is in SAT if it's of the form phi followed by hashtag followed by like any string of like junk. Okay, so you could just artificially pad out strings to any larger length without changing their satisfiability status. This is a bit of a technical point, but it'll make the proof simpler. The reason I want this is like, if I have the oracle for SAT for shorter languages, I want to know if like a shorter string is satisfiable. I can like put some junk at the end to make it back up to length n. So a consequence of these three great facts is the following, which I think kind of you implicitly needed on that one homework problem. Okay, so there exists a polytime transformation that basically puts all these ingredients together and turns like a decision algorithm for SAT on strings of length n into like a self-certifying version of itself. There's a polynomial time transformation, which I'll call, I don't know, self-certifying, that maps circuit C to circuit C prime. And C will be like an n-input circuit with one output that you imagine is solving the decision problem for SAT on formulas of encoding length n. And C prime is like some bigger, but still poly-size by virtue of only polynomially bigger circuit. It still takes n input variables, but like actually outputs either satisfying assignments or the word no. Okay, such that, you know, what I said, if C decides correctly SAT on strings of length n, then C prime does that thing I called star on that pane, also for length n formulas phi. Okay, so how does C prime work? It's got to kind of do star, so it starts implementing this search to decision procedure. And so one aspect of the search to decision procedure is understanding yes or no is a given formula satisfiable or not of a shorter length. You know, by using padding, it takes that shorter length string and artificially brings it back to a length n string, so it can use the circuit C to decide yes or no. And it can, you know, implement the whole process in that way and get the satisfying assignment. Okay, any questions about this? So this is a slightly technical series of observations. I mean, the ideas are the important one. The SAT has these nice properties, downward self-reducibility and search to decision property. And once you have that, the proof of Karp-Lipton is super short. Okay. So let's prove Karp-Lipton now. Okay, so what do we do? Well, we suppose that NP is in P/poly. And to spoil the punchline a little bit, that means SAT has a polynomial-sized circuit family. And the proof is going to involve guessing those circuits, but then also using this transformation to make them self-certifying, so that, like, even though we merely guessed them, we're kind of confident about the things that they output. That's going to be the key idea in the proof. Okay, so by virtue of this, there exists some poly-sized circuit family Cn deciding SAT. So we'll rely on that. In particular, it implies that there exists a poly-size self-certifying, you know, family. Which I'll call C prime sub n. Okay. And what do we need to do? What does the proof tell us we need to do? We have to show that polynomial time hierarchy collapses to the second level. So, okay, we want to show that pH equals sigma 2p. So I argued last time it's sufficient to show that pi 2p is contained in sigma 2p. Okay, that shows that everything above collapses all the way down to the second level. And that's equivalent to saying that the complete language for pi 2p, pi 2 SAT, is in sigma 2p. Okay, so we want to sort of flip the script and show that, oh, you can actually solve pi 2 SAT type questions using the opposite from natural order of quantifiers, sigma 2. Okay, and that lets you actually collapse the whole hierarchy down to sigma 2. Okay, so let's do that. Okay, so I'll now show you a sigma 2p algorithm for solving pi 2 SAT. Think of it as the alternating Turing machine model. I'll show you a sigma 2 type alternating Turing machine that solves pi2 set. So we're given like an instance of pi2 set. Well, something that looks like a pi2 set question. For all x, there exists y such that some Boolean formula psi of xy. And we want to know if that's a true statement. If it really is true that for all x, there exists a y such that psi of x of y is true. OK, so now I'm going to describe a sigma 2 type polynomial time alternating Turing machine that solves this problem. And let me just say, let's say let the length of this piece be m. Okay, and, well, what is m? I don't know. It's something that's less than n, the encoding length of this top thing. M is even smaller than the input length. OK, so what does the algorithm do? As I said, I mean, the key thing it does is it guesses these circuits, the self-certifying version, C prime. So we're going to existentially guess C prime m. OK, and let me just remind you here, I'm describing like a sigma 2 type Turing machine, which it first uses some existential guessing and then some universal guessing. So it's good we started out with some existential guessing. And this C prime circuit family is polynomial size family. So I mean, the description of this is some quantity which is a fixed polynomial in m, and m is smaller than n. So this is polynomial time. Yep.
Why do they have to guess that?
Well,
if we assume that in P and P slash poly, then we already know that there exist and they're constructible, so we can just take them.
well, the circuits exist, but this is the difference between non-uniform algorithms and uniform algorithms. Like we need to generate the circuit that does it. It's not enough for us to know that it exists for us to use it, because we're trying to construct a uniform algorithm.
And P slash poly is not uniform.
Right. So this is really like an existence statement. Like these circuits exist, and this is like saying there are some polynomial size circuits that solve NP, but like that doesn't put NP into P, because like how do you find those circuits in polynomial time? Now, it's not clear, but what we're going to show is, well, you can, if you have like some alternation power, you can guess those circuits. Still makes you a little unsettled because, well, I guess some circuit, but like, why is it the circuit that solves SAT? Point is, like, maybe it even isn't the circuit that solves SAT, but like, as long as it has the self-certifying property, then you're going to be fine, regardless of whether or not it really is the circuit that exists that solves SAT. Yep.
Do we know the polynomial that bounds C?
That's a good point. So like this is where you can use existential statements to your benefit. So like there exists a polynomial sized circuit family that does such less and such. What does that mean mathematically? There exists some number c such that there is an n to the c is a bad letter, k, such that there is some n to the k size circuit family that does this. And now I'm really describing a different sequence of algorithms, one for each k, like the one where it guesses circuits of size n squared, n cubed, n to the fourth. And one of those will work. Like the one where I've chosen large enough circuits will work. So I'm actually going to merely show there exists a sigma 2 algorithm that solves this problem, the one that guesses circuits of sufficiently large size vis-a-vis this. Yeah, that's a good point. That's one of these like funny subtle points. OK. Great. So at this stage of the game, it's used up its existential guesses. It hasn't used them up, but we're going to not use them anymore. We're only going to do universal guessing from now on. We've got these circuits that maybe supposedly solve SAT. And we're trying to, at this point, finally check this statement. Oh, we're trying to check the whole statement. That for all x, basically that for all x, this statement is true. The one underneath the above the brace. So how are we going to do that? Check that for all x, the thing underneath the brace is true. Well, we're going to use our universal guessing to kind of go over all x. And again, what this means is like we're going to try with computation branches all possible x, and we're only going to kind of declare success if all of them pass the check. Okay, and the final thing we have to do is like, we're out of quantifiers. We've used for exists and for all, but the last part is going to be deterministic. Deterministically verify, if you will, / check, using C prime M, that indeed, like, there exists y such that psi x, this is now fixed, these are variables, is true, i.e. that this thing is satisfiable. Okay, by basically plugging this into C prime, and well, if C prime actually outputs no, then the whole algorithm locally rejects, and if the C prime outputs yes, and outputs the satisfying assignment, then you accept. Oh, I should have mentioned that, like, okay, once that, an aspect of this is like once C prime outputs the satisfying, if C prime claims that it has a satisfying assignment and outputs it, you should also deterministically check that indeed the assignment it outputs satisfies psi, and reject if it was like cheating you. And that's it. Yep.
When do we use the parability of SAT?
It came into the existence of the self-certifying procedure because basically in the situation, like I could have done this in more than one way, but like basically I only want to assume that like I have like one circuit that solves SAT instances of one fixed length, which was M here. And in search to decision, you start constructing formulas that are actually shorter than M. So like it doesn't type check like your ability to plug them into this circuit to see if they're satisfiable or not. So you imagine that like you've set up the encoding in such a way that like if you have a short formula, you can artificially pad it back to length n.
Yes.
Yeah. Another way I could have done the proof is like had this algorithm guess all the circuits C prime 1, C prime 2, C prime 3 up to C prime M. That would have been fine too. But I wanted to mention this concept of padability. Yep.
The only real difference between this and our homework is that we use non-determinism to guess the advice instead of...
That's right. This is very similar to your homework. We use non-determinism to guess the circuits here, whereas in the homework, like you had a polynomial-sized collection of circuits, and you're like, one of these solves SAT, but I'm not sure which one. But then by like making them self-certifying in this way, like you can get around that issue. Okay, that's Karp-Lipton, a famous theorem. And now I want to tell you one more less famous but still cool theorem called Canons Theorem, named after a former CMU professor, Ravi Kanan. And it's like this. We know from the time hierarchy theorem that there exists a language L in time n to the 100. Yeah, n to the 100. That's not in time n to the 99. Nothing especially about this. But now I want to ask the same question, like, well, what if I make this non-uniform? Then do we know the same thing? And that's open. So here's an open question. Does there exist a language L in time n to the 100 such that L is not in size n to the 99? This is circuit families with order n to the 99 gates. That is open. We don't know. Because it's more powerful. It's non-uniform class. And indeed, also open is whether there exists an L in P such that this. We don't know. It's also open whether there exists an L in NP that has this property. Well, it's not open about P space. We do know that there exists an L in P space, okay, such that it does not have circuits of size n to the 99. Roughly speaking, that means it's because in polynomial space, you have like enough time to like enumerate all the circuits of size n to the 99 and diagonalize against them. So if we're trying to find like a language that's not too complicated, that definitely does not have circuits of size n to the 99, so for like the least complicated language we can find with this property is in P space. even though we kind of actually believe, I think, that like there's a language in time n to the 100 that doesn't have this property, or in P that does not have this property. Notice this is slightly different than going against P/Poly, where here we're going over against a fixed circuit size, n to the 99. OK? Canons Theorem, which I'll now tell you, improves upon this. It finds a language in like a smaller complexity class than P space that does not have n to the 99 size circuits. And what is this smaller complexity class containing this language? Sigma 4p. Okay, so like I will now show you something, a glorious use of like a rather complicated class in the hierarchy, Sigma 4p. This is Canons Theorem from 1981. This is it. There exists a language. Oh, in my notes I have n to the 100. Ooh, even better. OK, let's see if I can survive that. There exists a language L in sigma 4p such that L is not in size n to the 99. In fact, as you'll see in this proof, like this language is actually in sigma 4 time n to the 100. So it's not just polynomial time with a sigma 4 machine. It's like n to the 100 time. You just need n to the a little bit more time than n to the 99. OK, I mean, so let me just say, indeed, for all constants C, there exists an L in sigma 4 time n to the C plus 1, or C plus 0.1 if you want, such that L is not in size n to the C. You can even add almost everywhere, a point that I'll bring out in a second. Or you can put like quasi-polynomial time here, and you can say that L, it does not have polynomial size circuits of any size. Yep. Thank you. Yeah, that's very confusing. Thank you. OK. So this is what I want to prove to you. OK, so let me prove this to you. So I said we'll actually get something a little bit better. We'll get this. It's not. It's almost everywhere not in size n to the c. So we'll get a language L that's in sigma 4 time n to the 100, such that. OK, let me just expand the definition of L not in size n to the 99. It's a little bit tricky because this has like a big O built into it. So what is the opposite of the statement L has circuits of size order n to the 99? It's the following. If it doesn't have that, for all C, there exists infinitely many n such that L, when restricted to length n strings, has no C times n to the 99 gate circuit. OK? This proves this. But actually, I'm going to make it better. I'm actually going to prove a stronger thing. I'm going to prove for sufficiently large n, for all sufficiently large n. OK, so it's even better. OK, so it's not just like some super rare n's where this fails. Like basically, it fails almost everywhere. Let me call this property dagger, double dagger. OK, how am I going to prove this fact, that this L exists? Back in lecture 4, when we first talked about circuits, we proved this. It's kind of like the hierarchy theorem for circuits, that like for every size, basically, there's a language that's computable by circuits of that size, but not by circuits of like a slightly smaller size. And slightly smaller can even like mean like smaller by factor 4. So if you look back to that lecture, you will find that we easily prove by a counting argument this. In fact, for all n sufficiently large, literally bigger than 1,000, there exists a circuit C sub n taking n inputs such that two things hold about this circuit. One, it's small. It has size at most n4 n to the 100. And like it has no equivalent circuit of size less than or equal to n to the 100. Okay. So more size, even in fact there's 4, more size gives you more power. That's the non-uniform size hierarchy theorem. You can prove it by counting. Okay. So basically, if you were to stitch these circuits together into a language, roughly speaking, they would not be even in size n to the 100. So it seems like they definitely don't have like order n to the 99 size circuits. It's a little tricky though, because there are many such circuits like this, and like the language has to kind of definitively pin one down. So we're going to do it like this. For n bigger than 1,000, let Cn star be the lexicographically least circuit satisfying this condition I labeled star. So the circuit should have size at most 4 n to the 100, but no equivalent circuit of size at most n to the 100. Okay? These guys exist as long as n is bigger than 1,000. Let's Cn star be like just one fixed example for each n, the lexicographically least one. Okay, and like it doesn't really matter. I'll just write this. Define Cn star to be, I don't know, constantly 0 for n less than 1,000. It's not an important point. Okay, and now we've picked out one specific circuit for every input length, Cn star. So that circuit family defines a language. Well, I'll call it L star. Okay, and the L star is going to be my L that does the job. L star, yeah. And I claim this part is done. Basically, by design, L star satisfies this condition double dagger. Because for all n greater than 1,000, I mean, it requires circuits of size n to the 100. So therefore, no matter how big a constant C you make, there exists some sufficiently large point, which will depend on C, whereby you need circuits of size bigger than C times n to the 99. Just once n to the 1,000 is bigger than C times n to the 99. Okay, so the language by design has this property that, like, for almost all n, it really requires more than order n to the 99 gates. But what I have to show is that L star, we can put it into this relatively small uniform complexity class, sigma 4 time n to the 100. Okay. So let's do that. Okay, so it remains to show that L star is in sigma 4p. Okay? Actually, I'm just going to show this. I leave it as an exercise for you to show that it's in sigma 4 time n to the 100. Just watch my proof that it's in sigma 4p and just observe that it's all n to the 100 time. But I'm not so excited about that aspect. Sigma 4p is fine to me. Okay, so I'm going to do this in a sequence of lemmas. Lemma 1 is, we'll get to this of L star eventually, but let me do something simpler. First is this. Consider this problem. Given a circuit C, I want to check if it satisfies these two conditions I call star. Given a circuit C, check that it has size at most, with n inputs, check that it has size at most 4n to the 100. That's super easy. But here's the main one. Check that it has no equivalent circuit of size at most n to the 100. That task is in pi 2 p. Can somebody tell me why that's the case?
Every C that is lexicographically less that exists.
No, there's no lexicographic. I mean, I'll get to that, but there's no, star doesn't have anything to do with lexicographically anything.
Oh, yeah, so this is, yeah, so then for every circuit of size at most n to 100, there exists a string that it's different from ours.
That's right. Let me not write the proof, but let me just say the proof is like literally identical to this fact that we talked about both today and on Tuesday, that like same reason as, you know, circuit min is in pi 2 p. Okay, you have some circuit, you easily deterministically check that it has at most 4 times n to the 100 gates. Now the main thing is you have to check that there's no equivalent circuit of size at most n to the 100. It's basically the same as the circuit minimization problem. As you said, Alex said, you for all over smaller circuits of size at most n to the 100, and then existentially check that there's some x where the smaller circuit differs from C. Okay, so lemma 1 is done. Lemma 2 is given, again, an n-input circuit C. I claim that you can check if it's C star n in pi 3p. How can you do this? I'm going to use the fact that this is Cohen p to the pi 2p. Right, so since we're designing an algorithm, we'll use the most powerful sort of notion of the polynomial time hierarchy, which is the oracle version. Okay, and how do we do that? Well, what is C star and star again? It's the lexicographically least circuit that satisfies star. So we have to do two things. First, check that C, the input, satisfies star. Okay? And by lemma 1, you can do it with like one pi 2p oracle query. Now the main thing is we have to check that not only does C satisfy star, it's the lexicographically least circuit that satisfies star. But this is where we use like Cohen p power. So I mean, we universally guess over all, you know, lexicographically less circuits C prime, sort of lexicographically less than C, using kind of Cohen p power, and then use the pi 2p oracle and lemma 1 to check that C prime doesn't satisfy star. Okay, which is like well, to check that something doesn't satisfy star is really a sigma 2p problem, but we have an oracle, so we can basically it doesn't matter if we have an oracle for sigma 2p or pi 2p. We can just ask the oracle, does it satisfy star, and then take the negation of the answer. Okay, we're almost done. Good. So now we've climbed up to pi 3p, but we've sort of shown that we can identify C star. We have one more quantifier left. So finally, the proof that L star is in sigma 4p So we're given x, a real input. We want to know if x is in L star. What's the first thing we do? Yeah, we guess Cn star. Right? So we existentially guess Cn star. And then use our use up, let's say, pi 3p oracle to verify that guess. Okay, and now we've used up our sort of sigma 4 amount of alternation, but now we got Cn star. So we just, if you will, output Cn star on x. Okay, which by definition, Cn star like computes L star on length n strings. Okay, that's the end of the proof. Let me say a couple things. I know I'm going slightly over time, but first of all, there's like this amazing, like awesome plot twist that you can add here. It's like you can improve the whole theorem to like getting not just a language in sigma 4 that doesn't have n to the 99 size circuits, but a language in sigma 2 that doesn't have n to the 99 size circuits. And like the proof of this is like 5 lines long, and it's like legitimately funny. Like it will like make you laugh at the end. But I have no time, so I guess I'll put it on Piazza, and you can laugh in the privacy of your own room. And the other thing is I'm out of town next Tuesday. There will be a lecture, but it will not be here. I will like make a video for you guys to watch. So yeah, there'll be a lot of entertainment in the privacy of your own room until Thursday. I'll see you then.